Okay, so next we show that so this is about uniqueness when n is written as qd plus r with r in some number 0 to d minus 1, then this qr pair are unique. You cannot find different q and r that satisfy this part. Okay, so we prove it actually by contradiction. This is the usual technique to show uniqueness. So if it is not unique, there will be some problem. So suppose not. So suppose that it is not. Suppose it is not unique. Then what does it mean? So we can write n in two different ways. So let's say this is equal to q1 times d plus r1. And then n can also be written as q2 times d plus r2. Is that okay? Is that okay? Then what will happen? Yeah, let's see. What will happen? Then what do we know? Then, so this will imply what? So this is equal to n, this is equal to n. So the difference will be equal to 0. Am I correct? So does that make sense? Yeah. So we will have q1 minus q2 times d plus r1 minus r2 is equal to 0, right? Then what do we have? Okay, so we can actually write this as, so we put R2, R1 on the other side. So this is equal to R2 minus R1. Is that okay? Okay. Now, so what is the range of this R2 minus R1? So recall, each of the number of R1 and R2, they are between 0 and d minus 1. Is that okay? So the difference can be at most what? At most largest of them. At most d minus 1. Am I correct? So the difference can be at most d minus 1. Is that okay? Oh, sorry, at most d minus 1, so it is less than d. And how about the other side? At least what? What is the difference? The difference will be at least what? So difference could be negative, right? So it could be at least what? At least minus d, minus bracket d minus 1, right? So in any case, the difference will be strictly greater than d. Is that okay? Is that okay? So we will have what? We will have q1 minus q2 times d is a number that is strictly between d and minus d. Okay, all the numbers, so this is what? This is some integer times d, so it is a multiple of d. So what can be a multiple of d? 0 can be a multiple of d, d can be a multiple of d, 2d can be a multiple of d, minus d can be a multiple of d, minus 2d can be a multiple of d. Am I correct? So this q1 minus q2 times d has to pick a number here to represent. But now there is a restriction. This number is now strictly greater than minus d and strictly smaller than d. So what does that mean? So it cannot choose minus d, it cannot choose minus 2d. Strictly greater than these numbers. It cannot choose d, it cannot choose 2d. Strictly larger than, so strictly smaller than these numbers, right? So what does that mean? So this implies q1 minus q2 times d has to be equal to 0. because this is the only multiple of D that satisfies the constraints. Okay, good. D is non-zero, D is greater than 0. So some number times D is equal to 0. It means that this is 0. So this implies Q1 has to be equal to Q2. Is that okay? Is that okay? Now when Q1 is equal to Q2, then what does that mean? Then actually we will also have R1. So we also have R2 minus R1 is between that one and that one. It is equal to 0, right? So R2 has to be equal to R1. And then we get a contradiction. So we assume that there are distinct Q1 and Q2, but then we show that it cannot be distinct. So what does that mean? So it has to be unique at the beginning. Is that okay? So if you are okay with this, could you please raise your hand? Okay, good. So one part is easy. Okay, so this part is easy. This part is a little bit more difficult, but this is a very interesting observation. Yeah, perhaps this is the only non-trivial part of the whole proof. Okay. Now, although this division theorem is super simple, but then its usage, we will see that it allows us to show some amazing results soon. But before that, let us do some simple practices. So let us establish the correctness of the following statements. So we have the first statement. The first statement says, if A divides B, then, okay, A divides BC. Well, this may not need division theorem, but let's see. Okay, A divides BC for all C. Is it true? Okay, 3 divides 5. No, 3 divides 6. Okay, so 3 divides 6 times any number. Well, true, right? True. Why? Why? Okay, just use our definition of divisibility. So so A divides B means what? Means B is equal to AK, right? Is that okay? So it means that B times C is equal to A times K times C, right? So this is equal to A times K times C. So if a number can be written as A times another number, then we can write A divides BC. Okay? Is that okay? So that's it. So this is the proof. Okay. Let's do another one. Okay, so if A divides B and then B divides C, then A divides C. How do we prove? The same, super simple. Yeah, just translate back to what we know. So here, A divides B, B divides C. So A divides B, B divides C implies what? B is equal to, so B is equal to A times K1, and then C is equal to B times K2, right? Right? So C is equal to A times K1 times K2. Yeah, substitute B is equal to A times K1. So you bracket here. So this implies A divides C. Okay, that's it. Okay. The third one. Okay, if A divides B and then A divides C, then A divides any linear combination of B and C as B plus TC for every S and T. Okay? Is that okay? So this is also simple. Yeah, simple. Yeah, so simple. Let's write it down. Okay, so the proof is A divides B. So B is equal to AK1. A divides C. So C is equal to A times K2. So this implies what? This implies SB plus TC is equal to, just write it down, S times A times K1 plus T times A times K2, right? So this is equal to A times bracket of S K1 plus T K2. So this implies our result. Is that okay? Okay, last one. Okay. So suppose that C is not equal to 0. Then we will have A divides B if and only if AC divides BC. Well, let's see. Okay, let's see if we can get this result directly. So A divides B. This happens if and only if B is equal to AK for some K, right? So this is happening if and only if B times C is equal to AK times C for some C, right? So this is equal to AC times K. So this happens if and only if AC divides BC. Oh, so that's it. Okay. Key point here is that this is the part. This is the part that requires C to be non-zero. Okay. If C could be 0, then you can go to this direction, but you cannot go back. Okay. Yeah. And similarly, if C can be 0, then let me see. Yeah, then this should be okay. Yeah. This should be okay. Yes. Okay. So this is the step that requires T to be non-zero. Okay. Okay, so these are some trivial results, right? So what is the most non-trivial result? So this is about the property of GCD. GCD stands for the greatest common divisor. So this is an American term. So in English term, we call it HCF. Let's guess, what is HCF? What is HCF? In English, so this is called greatest common divisor, right? So English people, we don't call GCD, we call highest common factor, yes. Okay. But since GCD is now so popular, so even the English people, they use GCD. Okay. So what is meant by GCD? Okay. Okay. So GCD of A and B is defined to be, so we define this to be the largest number that divides both A and B. So normally we will look at numbers A, B to be non-negative. Okay, so usually. So usually we can denote this by GCD AB, or we can also denote it by small letter of GCD AB. Is that okay? Or sometimes when we are super lazy, we'll just write it down as AB. Okay? If it is very clear in the context. So some people will just bracket of AB. It stands for the GCD of AB. So for instance, what is the GCD of 12 and 40? So it is 4. Okay, good. What is the GCD of 5 and 18? 1, right? Is that okay? And what is the GCD of 7 and 0? What is it? 7. Excellent. So this is it. Okay. So first of all, some GCD property. So obviously, the first property is that it is symmetric. GCD of AB is equal to GCD of BA. Okay. And then the other thing is this one. So when the GCD of two numbers is equal to 1, then we will call these two numbers co-prime. Okay, maybe without a hyphen, co-prime. So 5 and 18 are co-prime. It doesn't mean that any one of them is a prime number. It just means that the two of them doesn't have any common factor other than 1. Is that okay? Good. Okay, amazing result here. Yeah. So we have this theorem. The GCD of A and B is always equal to the smallest positive. So it has to be positive. Linear combination of A and B. Okay. So what does that mean? Okay. So for instance, I have the number 5 and 18. Okay. Okay. So what can be a linear combination? So I multiply 5 with some number s, I multiply 18 with some number t. Okay. So for every s and t, that are integers, then any s, any t, if you plug it in, then this will be a linear combination of 5 and 18. So 5 and 18 can create what? It can create the number 5. So 5 is one of the linear combination because I put 1 here, I put 0 here, and it is a linear combination of them. So I can also have 23. I put 1 here and 1 here, then I get 23. Is that okay? I can have 0 here. Okay, but here we want to talk about smallest positive linear combination. So we will consider only linear combinations so that the resulting thing is a positive integer. So 0 is a linear combination by putting 0 here and 0 here. Is that okay? But we won't consider it as a candidate for the GCD. But how about, so we can also put minus 1 here, right? So minus 1 here, so we will get 13. Is that okay? And then if I put minus 2 and 1 here, then I will get 8. 8 is also that one. We will also get 3. Is it okay? So we will get many linear combinations of this 5s plus 18t. But among all the possible linear combination, the smallest positive one will be the GCD of this one. So it turns out that 5 and 18, the GCD is equal to 1. Can we get? So let's see. How can we get something that is 1? So like this one. So perhaps I put S is equal to 11. Okay? S is equal to 11. And then T is equal to minus 3. Is that okay? 5 times 11 is equal to 55. 18 times minus 3 is equal to minus 54. So after adding up them, we get 1. Okay. And then we know that we don't need to check anymore because 1 has to be the smallest positive integer. So in that case, GCD of 5 and 18 is equal to 1. Okay? Well, strange, right? Very, very strange result. And it looks that, how can we prove this? So the proof turns out that the major part of this proof is something that I have wiped out. This is the division theorem that we have shown. Simple, any number has a unique quotient and remainder, and that is what we need to prove this. Okay, so let's prove this. Okay, how do we prove? Okay, so the proof. Let's try. Let me get this one. This one. So the proof, the idea is to show that, okay, so this is the theorem, right? So first of all, we call this part equal to M. Okay, and then we don't know whether this is correct or wrong. Okay, M represents the smallest positive linear combination of A and B. And we want to show, we don't know whether these two are correct or wrong. The proof established that they are equal. So this is still a question mark before we prove it. So we want to show that M is really equal to GCD of A and B. And the idea here is that we are going to show, so this is the target. So the target is, let me write down, we will show M is greater than or equal to GCD of AB, and M is going to be smaller than or equal to the GCD of A and B. Is that okay? Is that okay? So first, so 1 and 2, we need to show these two things. So which one is easy? One of them is actually super easy. So what is M? M is equal to some S times A plus T times B for some S and T, right? So this is what M is really, because M is a linear combination. What do we know? GCD of AB divides A, GCD of AB divides B. So GCD of AB divides any linear combination of A and B. This is what? This is number 3 there. GCD of AB divides some number. So if A divides B, A divides C, then A divides the linear combination of them. Okay, so we know what? First, we know that GCD of AB divides A and divides B, so it divides M. Okay, and then M is positive. Then what do we know? We know that GCD of A and B has to be smaller than or equal to M. Does that make sense? Does that make sense? Yeah. So we get what? We get 2. So 2 is correct. Okay. Now, how do we show that M is greater than or equal to GCD of AB this time? This is going to be strange. This is the smallest linear combination of A and B. And how do we ensure that this smallest number is still large enough to be greater than or equal to GCD of AB? Now, we don't know how large it is. We don't know. We don't know. Does that? Sorry, not 2. Sorry, 1. Sorry, I make a mistake, sorry. So we are showing 1, sorry. So here, GCD seems to be a small number this time, but then we want to show that M is less than or equal to GCD of A and B. In fact,